Okay, so here we're going to be talking about interesting technology that we have in IBM's Power AI. And here's the hook for the technology. Imagine you've curated a big data set that you spend a lot of time collecting all this data. You've built a deep learning model that will pull all the information out of it, and you can train on it and that kind of thing. And you've gone through the training. You think it's going to work. All of a sudden, you blow up with an out-of-memory error, and what do? You've already kind of compromised. Maybe you've scaled down your data sets, these kinds of things. What do? Well, we're going to be talking about that. So we're going to be talking about essentially a way of utilizing host memory to overcome some of these problems where you have kind of a limited memory set on your GPU. So one of the main kind of problems, GPUs have a small amount of memory. Back in May, NVIDIA released the new version of the Volta. It has 32 gigabytes of memory on it, which is a lot. They did a good job with that. They doubled the amount of memory from 16 to 32, which is fantastic. Except for 32 is still way smaller than how much you can have on your system. You can have 1 terabyte, 2 terabyte system memory. So this is still kind of quite a bit behind, and a single CAT scan can be up to a terabyte of memory, right? So 32 gigabytes is great. It's still pretty small, though. Our neural networks are getting wider, getting bigger. They do a lot more stuff. We used to have just a few layers, and we've got hundreds of layers in some of these models. And that alone takes up a lot of space, and we'll see why. We also have the data we have itself is huge. We have high resolution images. We have a lot of them. I mentioned a single CAT scan could be up to terabyte, and hospitals have a whole library of those, right? How do you use that? We could scale it down really small, and you kind of juggling with the GPU memory is what you have to do today. So if you have this limited amount of GPU memory, you have to really know what it's being used for. You have to manage it very closely. It's very important to know. You don't want to be wasting any of that memory. So this is a representation, a typical TensorFlow model. What's the memory being used for? So we've got our input data, obviously. This is if we're talking about images. Give that as an example. This is your image set that you're working on in a particular operation. Maybe you've got it batched up. Oop, wrong button. Maybe you've got batches of them, but still there's a certain amount of GPU memory you're using for that. The kernels are the actual GPU code that you use to calculate your loss or your ReLUs or whatever. That the actual kind of code, we can't get rid of that. It's important. We also have the neural network itself. That has to be resident in the GPU memory. We can't really get rid of that unless we kind of scale down what we can actually do with it and shrink it down. We're trying to not have to do that. And then we've got our layer outputs. So for each layer, it does the calculations, and then there's a certain amount of data that's passed on to the next layer. We call this like the tensors. This is the output of each layer, and these kind of accumulate as we go. So it's important to kind of understand all of that, so we can kind of try and find ways to reduce what we're doing, at least manage it a little better. So let's take a look at this a little bit closer. Maybe a solution will present itself on how we can either manage things better or reduce the amount of memory that we're using. So we'll just kind of look through the way training works today on a GPU. So we've got our neural network here, and we're kind of going to go through the training steps. So first thing it does, it goes through the first layer of the network. It does the calculation, generates the first tensor, and kind of puts that in memory. And here we're not going to compromise yet. We're not going to shrink down our data set. We're not going to do anything else. So this is kind of a scenario where we're out of memory. So, but we're not yet. So we have the tensor 1 is cached in the GPU memory, and then that's passed forwarded to the second layer. Then there's a tensor 2 that's generated. That's in memory as well. We'll go to the next layer, and then oh no. Tensor 3 is outside of the blue box there, which represents the GPU memory. Now we're out of memory. So the reason I'm kind of showing this is kind of a good visual representation to see, oh, maybe what we're doing here is a clue on what a solution could be. So we've got the tensors are kind of hanging around a little bit. So the reason they hang around is by the time we get to the loss function, we'll need these in memory for the back propagation stages, which are back kind of this way. We need these tensors to calculate again. So we can't just delete them after we go forward. So we need them around, but maybe we could do something different. Maybe we can cache those out to system memory until we need them, because they're just kind of sitting around there and they're not there. They're not needed until they're needed, right? So let's try to come through a solution here that we put those tensors back out to system memory. Maybe that's a good solution. So this is how maybe that could work, and we'll walk through this. So if we have the first layer here, we've got the first tensor generated after the first layer. Let's try to swap that down to system memory, and then we still kind of have all our GPU memory free. We generate the second tensor based on the second layer there, and then we'll move that one down, and we'll kind of continue on with tensor 3. And by the time we get to tensor 4, everything still fits, right? We didn't have to compromise on shrinking our data or ripping out layers of the model there. So we're in tensor 4, we're kind of at the end of the layers set here. We can actually kind of keep that one in GPU memory because after the loss function is calculated, we're going to need it back anyway for the back propagation phase. So so we get back to the back propagation. We can actually kind of get rid of tensor 4. Now it's kind of garbage collected. And then we swap back in tensor 3, 2, and then 1. And so that's kind of the idea. Maybe that'll work. I think it solves a couple things. We conserve our GPU memory. We've not compromised on the size of the data set or the tensors, and we have not compromised on the size of our neural network. So we've actually implemented this into an extension for TensorFlow. We call it TF-LMS, TensorFlow. LMS is large model support. It's called large model support, but it's also can be used for large data sets. It's not only for larger models, right? So this is another representation of the actual TensorFlow graph. So when you're doing a TensorFlow model, you kind of build the graph first, and then you execute the graph, and it goes through the training. So how this works, you kind of define your operations, and then the output of A goes into the input of B. You can kind of define whether your operations are on the GPU or on the CPU. We generally want them on the GPU. It's kind of the accelerator. That's where you want your operations to happen. What we've done with TF-LMS is we've added swap out and swap in nodes primarily on the CPU. So what happens is the output of operation A goes into a swap out node. It swaps out those tensors like we just saw. That goes into a swap in node, and then that comes back out to the GPU, swaps back in the tensor when it's ready. If you notice, there's actually a dotted line here as well. That's a control vector. So what the point of that, you don't want to swap out and immediately swap back in. You want to have some sort of control mechanism to say, oh, just swap back in when I need you. Swap back in when at the last possible moment I want to conserve my GPU memory for as long as I can, and then swap back in. So that control vector we've enabled with a couple different APIs to be able to control that when that actually happens, so it can stay in system memory until you need it. Okay, so that's we mentioned the extension to TensorFlow. That's kind of that former representation was kind of the graph level view. This is kind of what it would look like in the code. It sounds like it might be a hard thing to implement, but it's I actually kind of hesitate to put code up here because put people to sleep, but it's actually, I wanted to show how easy it is to actually implement. So in TensorFlow, kind of the two main high-level API sets that people use are either Kris or the Estimator API. There's a couple different ways of using TensorFlow, but this is kind of ways of enabling it in these two models. So in Kris, you pretty much kind of just enable a LMS Kris callback object, and you pass that into the model fit generator API, and that's it. You're good to go. There's a couple other optional things you can use for the control vectors, but there's defaults in there that work pretty well. It's a little bit more complicated for the estimator API, but not much. There's a name scope that you have to define in order for this all to kind of work. And estimators, it's all about exclusive name scoping on everything. So you've got to set up the name scope, and then you can pass along into the or there's an LMS hook API that you use, and you pass it into the train classifier there. So that's it, and that will enable the Python module to do what we were just showing in the representation previously. Pretty easy. Some code changes, not nothing, but it's pretty minimal. We've kind of focused on the main usage models of TensorFlow. So what's possible? What's some of the benefits? So with TFLMS, the goal was to enable larger data sets, larger models. So we took one of Google's benchmark codes that they've got, the TF-CNN benchmark. We call it high performance benchmark internally. There's a couple different names for it, but it's a benchmark code that has lots of different models built into it. Like there's a GoogleNet, ResNet, a couple different flavors of ResNet in there. We enabled that with TFLMS, and we've kind of had some of these numbers here with higher resolution. So with GoogleNet, we got 2.5 increase. 2.5 times increase in the maximum image resolution during the training. ResNet 50, we got a 5-time increase in batch size, so that a higher batch size will allow you to converge quicker. And then in ResNet 152, we got 4.6 increase in batch size, or similar results there. And these are the ResNet ones are much larger size models. So having that much larger of a batch size increase in an already large model is pretty significant. We've also enabled a 3D UNet brain MRI classification model. We saw the 2.4 times increase in image resolution there. I'm going to jump into that one a little bit more because that one's kind of a really interesting use case. So 3D image segmentation. What is image segmentation? So you're probably familiar with like the dog classifier demos, or just the basic. You've seen a lot of those. What kind of cat is this? It's classifying the whole image. Image segmentation is used when you need to find multiple things within a single image. So you kind of have so every pixel on your image needs to have a class, right? So a good example would be if you have a satellite image and you need to be able to pick out a river versus a road, right? So you don't want to just say, oh, this is a picture of a river, when it also has a road in it. You need to be able to segment out the image, and those type of models are used for that. So the 3D UNet part of it is, so 3D means that we're working with 3-dimensional images, so like entire scans, for example. And then the UNet is just kind of the slang for kind of how the image or the model is built. There's a interconnected up and back to it, so it's kind of a U. So, but 3D UNet models generally have very high requirements on data. So usually the 3D images have a lot of data already. If you think about a 2D image versus a 3D image, there's much more data there already. Especially if you're not even talking resolutions just yet. So. And then also the interconnected aspects on it, you have to keep a lot of the data around a lot longer as well. So it's really hard to get these models to train higher than a batch size of 1 if you have any type of data whatsoever that's not just shrunken down to unusable. So so really good use case for our TFLMS to try and see what we can do here. So there is what is the International Multimodal Brain Tumor Segmentation Challenge, Bratz for short. It's an annual challenge that they hold to try and push the state of the art of these type of models. There's so there's a contest, and whoever can write the best model and have the best accuracy, have the best data density, that kind of thing. So yeah, so it's kind of pushes the state of the art there. So there's a lot of submissions in there, and we actually kind of found an interesting submission that had a Kris model already, and it finished third, I think. Somebody from the University of Pennsylvania was doing the work. So we were like, that's a good place to start. So we took that, we enabled TF-LMS. Well, actually, first I think the initial model didn't have a TensorFlow backend, so we switched the Kris model to use a TensorFlow backend, and we added TF-LMS to it, and kind of tuned it up and see what we could get out of there. So here's some of the results. So the challenge uses these dice coefficient scores in order to kind of score how well the model is doing versus the ground truth, with the ground truth being the images that an actual doctor looked at and determined a tumor, you know, and the core of the tumor and the features of it. So then we train the model against this data set, and then we see, you know, how it did versus the truth. What this is showing is the benefits of a 2 times resolution difference in the image itself that we're training against. And we saw from the earlier chart that with our TF-LMS enabled, we got about 2.5% or 2.5 times the higher resolution. So this is the kind of benefit that you'll see from a 2 times resolution jump in these type of training. So you just have that much more information in your data set that you can pull from. That's a huge jump. So, you know, you might not be familiar with how the dice coefficient work, but essentially higher is better. And these lines kind of mean specific things, but higher is better for all of them. And across the board, higher resolution will get you higher results, higher scored results on those. And the challenge, there's 3 of these because the challenge actually kind of scores, you know, identifying the tumor and then the core of the tumor and some of the features in it as well. So there's actually 3 different scores, but definitely higher scores throughout, right? So this is the kind of benefit that a higher resolution can give you in your training runs. So one thing that we didn't talk about is like, we know, what's the catch here? Or like, why isn't anybody doing this already? Right? It's pretty fundamental, but swapping can be slow though, right? Think about it in your laptop. We've all gotten to the scenario we've run out of memory on our laptop, right? And start swapping to disk. Even if you have a fast disk, that's a recipe for a blue screen, right? It's gonna be bathed in blue light very shortly if you start swapping. So I'm actually gonna toss it over to Kris here in a minute, but you know, she's gonna talk about some of the specific hardware features in the OpenPOWER boxes that actually enable this to happen in a good performance. So I'll pass it over to Kris. Thanks, guys. Up and down, and the other one's the laser.
All right, so my name's Kris Murphy. It was on the beginning slide, but I also work on the Power AI team with Jason. So yeah, swapping is slow, but this is where we're going to talk about why this matters, or why Power 9 matters, right? So I'm sure you guys have heard a lot about Power 9 and our unique hardware features that we have in the AC922 or the GPU box, but this is what a typical non-power system looks like for our connectivity. There's a couple of things to note here. If you look at the bus between the system memory and CPU and how fast that bus is, about, you know, average or typical of 76 gigabits per second. And then look at the link between the CPU and the GPUs, right? So here they have PCI, and in most cases it's PCI 3 these days, Gen 3. Not only is that bus only 32 gigabits per second, but also in a lot of systems, you typically have 2 GPUs per PCI link, right? So if you're doing things to both of those GPUs at the same time, you're sharing that 32 gigabit link. So that's a huge bottleneck. So for this type of system, if you were doing this swapping of tensors in and out, you know, and you have a bunch of GPUs, you know, sharing these PCI links, that can be really, really slow. And so you can do LMS on this box. We've attributed TensorFlow LMS to a PR upstream. You could download it. We've ran it on x86 boxes. It works, but it is slow. So if we compare it to what we have in our OpenPOWER Power 9 that IBM builds, if you look at the bus between system memory and CPU, we've got 170 gigabits per second. It's quite a bit faster there. And then if you look at the links between the GPU and the CPU, we have NVLink 2.0. And we have one of these links per GPU. So they're not sharing this, right? So you get 150 gigabits per second. And then they also have NVLink 2.0 between the GPUs. Lots of other boxes also have that NVLink between the GPUs. So they might claim they have NVLink, but they don't have NVLink between the CPU and the GPU, right? So if they can do things where they only have to be in the GPU and they're not transferring things back and forth to the CPU, it's all good. But for a case like LMS, where you want to be swapping things between the CPU and the GPU in order to take advantage of your system memory, that bus is really going to matter. So here we're going to show some pictures, and these are pictures from using NVIDIA's NV Profiler, where you can look at when you're doing a model run in training and see the brown spaces. Those are memory copies. So you can see where memory copies are happening. And then the bottom line here is your GPU utilization line. So this top image here is on that PCI connected system where you have the PCI link to your GPUs. And when you run that 3D UNet test that Jason was talking about, if you run that on that x86 system, you can see a lot of white space in your GPU utilization line. That means all those white spots are times that you're waiting for your data to get transferred into your GPUs. So you're not fully utilizing those GPUs and you're sitting and waiting. So that's where swapping is slow in this case. So let's compare this to what we have if we run this on our OpenPOWER system. So this is the exact same run. So if you look at how long this is on our box here, it's a lot shorter. Total time is a lot shorter, right? And that's because if you look at our GPU utilization here, our GPU is busy almost the entire time, right? Because we're not waiting so long for all of that swapping to happen into our GPU, right? So that's where we get those speed ups, right? And here you can see the connection. So you can see where it's the exact same stuff going on in both. The blue lines connect here. You can see the different pieces of the model when they're running, and you can see, how they compare there and how much more spread out they are on the PCI connected system. So a little bit more details. We have a few more graphs here on the difference it makes. So this is the impact on the epoch time on these different systems. So here, lower is better. You don't want it to take very long. You want it to take shorter amount of time to run an epoch, right? So the first bar here is on the AC922 with our NVLink 2.0, and then you compare it to a GPU server with PCI. And in these cases, we're only using one GPU at a time, right? But remember on that PCI connected box that sometimes the two GPUs might have to share that same PCI link. So this last bar here is what would happen if you were using that other GPU for some other work that was also using that link. So now that link isn't fully available for your GPU that you're training. Now your epoch time goes up even more because now you have that shared bus contention. And this is effects of GPU utilization. So here we want higher bars because we want our GPUs to be fully utilized, right? They're usually the most expensive part of a GPU system is the GPU, so you want to be taking full advantage of your GPUs and using them as much as possible, right? So the green bars are GPU utilization, and the orangish colored bars, that's the memory copy throughput. So you can see, running this on the AC922, what we get there, and then in the middle, this is, the PCI connected box if you don't have PCI contention. And then at the end, when you do have the PCI contention, you can see that the memory copy throughput goes down, and hence so does your GPU utilization because you're sitting around and waiting. So we did want to look at and try and figure out our overhead of doing swapping, because yes, it's faster on the AC922 than it is on the PCI connected boxes, right? But there is still some overhead, right? So because we now have those 16 gigabit GPUs and the 32 gigabit GPUs that NVIDIA makes, so we run these tests on the 16 gigabit GPU with swapping, with using LMS, right? So using an image that's too big and we have to swap in and out, right? And then we compared to running that same image size, running that same image size on a 32 gigabit GPU where we didn't need to swap, right? So that we could tell exactly how much overhead we had for doing this swapping, right? And our overhead wasn't really that bad. When we were doing 1.4 x the image size, it was like 3% overhead, and bigger, as you go to bigger and bigger images, you're going to be doing more and more swapping or bigger swaps, right? So by the time you get up to the 2.4x, your overhead's at like 27, 28% overhead. So it does get more, but it's still, if you consider that you could do an image that wouldn't be possible without large model support, right? Yeah, so this is explicit. So with the LMS stuff, we have some Python modules that are used for doing explicit swapping. And you can, with that control line that Jason was talking about earlier, you can sort of have it swap in a couple layers before you need the images. So you can do some, so it's swapped in so it's already there instead of waiting until you actually go try to use it, basically like prefetching it into the GPU a little bit. And those are some of the things that you can tune. There are tunables on LMS that you can do. So you can tune how early you want to swap things in and out to balance being able to do the maximum amount versus, having stuff prefetched. So that's what explicit swapping will do for you versus, using some of the CUDA stuff and waiting until you actually go touch it for it to come in. So the future direction of large model support. So coming up pretty soon, we're expecting TensorFlow 2.0, and there are some changes that will be coming in TensorFlow that will have some impacts on TensorFlow. Eager mode will be on by default, and then TensorFlow.contrib will be sunsetted, and that's right now. So I said we put this up in a PR. That's where it is right now. We submitted it to TensorFlow contrib because that's pretty much how they wanted you to contribute to TensorFlow in the past, and they're getting rid of that. So we're looking at other ways to integrate this into TensorFlow and where it's going to belong. In the meantime, we may have like our own repo that we have out there for storing it in so you guys can all access it. It also is built into our Power AI TensorFlow. So if you have Power AI, we already have LMS built in there. You don't have to like go download it, but if you are building your own TensorFlow, you can go download it and build it in as well. But we might integrate it into TensorFlow's grappler, and if people want to contribute to this and work with us on this, we're open to contributions and people working with us on that portion of it. And we are also continuing research into this. We have a bunch of research teams that work on things for Power AI, and then they give us input into our development team, and we take and productize some of those things. Research has a new version of TensorFlow LMS that is doing some different things with the graph modifications, and we've done some early experiments with it. Like we showed earlier, you can do currently 2.4 max resolution size. Our early experiments show with the new version, we'll be able to do 6.9x. So that's a big bump with the new version. We're still early in that and figuring out when that will be part of Power AI, but look for definite improvements in that area. Also, LMS is not just for TensorFlow. We went over specifically how it works in TensorFlow and the 3D UNet model we ran with TensorFlow, but we also have large model support for Caffe. That's already also built into Power AI. And coming soon, we will have large model support for PyTorch. Is that targeted for our next release? An early version of that on our next release of Power AI. You should be able to start playing with the PyTorch large model support. All right, so this is basically the summary. I guess we're already at maybe a little fast. So sort of what we went over is you can use tensor swapping to overcome GPU memory limits, right? How many minutes do I have? Are you pulling up signs? Oh, I only have 1 minute. Okay, we're not as fast. Sweet. It allows us to train deeper models. If you wanted to do a model with more layers, it enables that. Or also higher resolution data, like brain scans, other medical images. A lot of them are too big to fit. A single image doesn't fit in your GPU. So this allows you to use bigger images without having to compress those images and lose parts of your data. And then also you could potentially do larger batch sizes, which might enable you to converge faster. And NVLink 2.0 between the CPU and the GPU allows you to do this without it being as slow as it would be on a lot of our competitors' boxes. So we also have a bunch of links here for more information. That's the PR that we talked about at the top for TensorFlow. There's a research paper that a research team did on large model support. If you want to know more about that 3D-UNet case study, we have a whole blog post on it and a lot of the information on how that was ran and the different results. And then information on NVLink 2.0